Example 4. You have been asked to design a 1-liter oil can shaped like a cylinder. What dimensions will use the least material? Why is this an optimization problem? Exactly, we're trying to minimize something. In particular, we're trying to minimize material. So go ahead and set up the problem. Tell me what we're trying to find, what the goal is, and what we're given. So if I were just starting this problem, I would probably say what we're trying to find is the dimensions, and what we're trying to minimize is the material. And what we know is that the can is 1 liter. But we can actually be more specific about all 3 of these things that I just said. When we say dimensions, what are the relevant dimensions of a cylinder shape? Well, radius and height are the 2 that come to mind for me. So what we really want to find are the radius and the height of the can. When we say we want to minimize the material, I've got a picture of the can here. Maybe this will help you. We're making this can out of metal, right? The material is the metal. Looking at the shape, what part of this cylinder is actually metal? Right, it's the outside part. In other words, mathematically speaking, the material around the edges is the surface area of the shape. What I'm really trying to minimize is the surface area. If I want to use as little metal as possible, I need the surface area to be small. So instead of saying that our goal is to minimize the material, let's be precise. We want to minimize the surface area of this shape. And when we say this can is a 1-liter can, what are we really talking about? Are we talking about the surface area? No, we're talking about the volume. So instead of just saying this is a 1-liter can, we should say the volume equals 1 liter. And I'm going to give you another fact, actually, which might be useful, which is that 1 liter is the same thing as 1,000 centimeters cubed. So instead of saying the volume is 1 liter, we could say the volume is 1,000 centimeters cubed. I now feel like we have a good understanding of the basics, and we're ready to start the problem. Remind me again, when we're doing an optimization problem, after we've interpreted everything, what's our next step? Yes, we want to write a function whose output is the thing we're trying to optimize. In this case, that's surface area. So we need to know how to calculate the surface area of a cylinder. Remember before we talked about breaking up surface area into a bunch of pieces? I'm going to do the same thing with this shape. The surface area, or exterior of a cylinder, has the top and the bottom, which are both circle shapes, and then it has the wall, which if you unfold is actually a rectangle. The 2 circles have area of pi r squared, and a rectangle has an area of length times width. So this expression is an expression for surface area. But remember, we're trying to get an expression for surface area with only 1 variable. Right now I have 3 variables, so I need to start simplifying something before I really have my function down. For one thing, when I talk about length times width, well, if you think about what this rectangle is, it's this exterior that kind of wraps around the shape. So actually the width, this little distance here, of the rectangle is the same thing as the height of the can. So let's use height instead of width. And I'll just replace that right here for now. And now think about what the length really is. The length of this rectangle is the distance all the way around the can. In other words, it's the circumference of the circle. And we know what that is. The circumference of the circle is 2 times pi times the radius. So the length of this rectangle, whose surface area I'm trying to calculate, is the same thing as the circumference. And I'm going to actually replace L with this expression right here. You might see why I'm doing this. I notice that this expression has an r in it, and I'm trying to get rid of some of my extra variables. When I make that substitution, I end up with this expression for the surface area of the can. Notice that I just combined these 2 terms into 1. Now, this still isn't quite good enough because I still have 2 different variables, r and h. So I have to look back in the problem here. The problem must tell me something else about the relationship between the radius and the height. And it does, but in kind of a sneaky way. The one piece of information we haven't used yet is this whole volume business. Well, think about what the volume is. Volume of a cylinder really depends on its radius and its height. And we have a formula for how. The volume of a cylinder is the area of the base times the height of the cylinder. And the area of the base is pi r squared because the base is a circle. Notice how I'm writing this volume formula indented off to the side. I've put it off to the side because I'm about to rearrange it and then plug in back into the S function, and by keeping the S function out front, I've organized my work so that you can follow. This is kind of like a side trend. Now that I see what the volume is, I can use this 1,000 centimeters to create a second equation that has R and H in it. Because the volume is 1,000 centimeters cubed, pi r squared h must equal 1,000. And I can rearrange this expression to get h by itself pretty easily. H has to be 1,000 divided by pi r squared. All of this is actually technically part of the given information. It's just kind of a rearrangement. It's a couple steps down the line. Since I know this has to be true, I'm trying to create this expression so that it only has one variable. Look what would happen if I replace h in this expression with this expression right here. We now have a formula for the surface area that only has one variable. That variable is r. If you want to see where this, make sure that you can see where this comes from. The 2 pi r just came down. Remember, that was the two ends of the cylinder's area. This 2 pi r represents the length of this shape, which was the circumference of the circle. And this 1,000 divided by pi r squared represents the height, which was the width of the rectangle. Okay, all of that work just to get our function. Think about the steps for doing an optimization problem. I have a function for surface area. What am I going to do next? Yes, endpoints and critical points. Now, before I actually go there, I'd like to simplify this expression. You notice that you can put 2 pi r along with the top of this expression, and actually one of the r's will cancel out. And there's the simplified formula for surface area. So endpoints are asking the question, are there any restrictions on our input variable? Our input represents the radius. Are there any rules about what the radius number can or can't be? Any limits on it? Yeah, I would say 0 is a lower bound because radius, the distance, it has to be a positive number. You can't have a negative radius. So I would say r equals 0 is a lower bound. But as far as we can tell, there's no upper bound. We could make the radius as big as we want as long as we minimize the material. So to check the endpoint, I'm going to plug 0 into this function. But I notice actually there's a domain restriction. So 0 is not going to be a contender for the ideal radius, which is good news because we wouldn't really have a can then in the first place. But it's part of the math, so let's stay consistent. Critical points. Let's find the critical points. How do we do that? Yep, we just set the derivative equal to 0, and then we solve to get r by itself, which I'll do by subtracting 4 pi r, and then cross multiplying. And following the algebra out, I end up with r cubed equals 500 divided by pi, which is going to be an irrational number. But to get r by itself, I take the cube root of both sides, which when I plug into my calculator gives me 5.419. And that should be the r value. That is the r value of the max or min of my surface area function. You should remember by now we're going to have to prove that it's actually a minimum. But before I look at the second or first derivative test, let's go ahead and figure out what the actual surface area would be by plugging this r value back into the original function, which was this one right here. I recommend you use your calculator. So when I plugged back in, I got a surface area of 553.581. Think about units for a second here. We used centimeters cubed for volume, so we actually have centimeters as the units for radius, and the surface area will be centimeters squared. This seems like a pretty big surface area. So if this is the minimum surface area, I'm a little worried because that seems large, but let's check. And the way to check, of course, is first or second derivative test. I'm going to try first derivative test this time. We've been using second derivative test for the last couple examples. To do the test, to prove that this really is the minimum, I set up a little number line and I plot my critical point, which is 5.419. And then I'm going to plug back into the first derivative and to check the sign. Oftentimes you can use your calculator to help you with this or just kind of estimate. A number smaller than 5.419 that I could test would be like 1. And if I plug 1 back into the first derivative, which is this expression right here, the first term will be something like around 4 times pi. And the second term will be negative 2,000. Well, negative 2,000 is way bigger than 4 pi. So I end up with a negative answer in my first derivative when I plugged in a number before my critical point. Now I need to test a number after my critical point. Well, what if I tested like 2,000? If I test 2,000 right here, you can see that this number, because when you square it on the bottom, is going to be 1 over 2,000. This is going to turn into a very small number. And a positive number minus a very small number is going to be a positive answer. So when I test a number on this side of my critical point, I got positive answers. So if the derivative is changing from negative to positive, my original equation is changing from decreasing to increasing, which shows me that this is in fact a minimum. That's the first derivative test. All right, we've basically finished the problem. I just need to know how to write my answer, which means I'm going to refer back to what the original question was actually asking me for. And I remember now it was asking for radius and height. Well, I found the radius. I need to find the height. How could I find the height? Yeah, there was a formula for it. We used the volume to derive a formula that will tell me what the height is now that I know the radius, and I'm just going to plug in right there. So in conclusion, when I plug in, I get a height of 10.839 centimeters, and that's your final answer. You could make it a sentence by saying something like, the dimensions of the can should be, and then just tell the dimensions. Awesome. That is it for this video. By now you should be pretty comfortable using derivatives to set up and solve optimization problems. You should know by heart the steps that we talked about, and you should be able to identify what makes something an optimization problem. We will continue to practice, especially the geometric skills, and we'll do a bunch of more examples in class. Have a good night.